This week we're going to cover Direct Memory Access DMA, which is a pretty cool concept. We'll start with an introduction, then we'll see how does it work from peripheral to memory interaction between the DMA, and then also from memory to peripheral. And if you recall the simple system plus DMA, we have here our CPU that can interact with the peripherals here using the buses, and then they can send interrupts back to your microprocessor. But you also have this DMA, Direct Memory Access controller, that can interface your peripherals and also send commands or information to your CPU. So the DMA goal is to provide high-speed data transfer between peripherals and memory, and between memory and memory. Data can be quickly moved by DMA without any CPU action, and this keeps the CPU resources free for other operations. So pretty powerful. You have two DMAs available on the STM32F4, and you pretty much can do peripheral to memory, or memory to peripheral, or even memory to memory interaction. Some features. So already said or mentioned that you have two DMA controllers with 16 streams total, and where you have 8 streams per controller, and then the streams can have up to 8 channels or 8 requests in total. You have an arbiter that handles the priority between the DMA requests, and you can also have a FIFO if you have information coming faster than what you can process. You can store that information in a buffer. So already said the type of transactions that you have with the DMA: peripheral to memory, memory to peripheral, and memory to memory. This is the DMA block diagram. So what you have here is, so remember, you have 8 channels and 8 streams. So this is one DMA controller, and then you have the part here that controls the priority of your streams, and then you can enable or disable your buffer here, and then you send the information either to memory or get the information from memory, and you send it to the peripheral or you receive from the peripheral. For channel selection, we are going to use these two tables over here. So depending on how you want to interact between the peripheral and the memory, you need to select the respective DMA. So we are going to do an exercise with ADCs, and we are going to use the ADC number 3, and that one is going to use channel number 2 and either stream 0 or 1, and is going to use DMA number 2. And then we're going to use a DAC, and is going to be from memory to peripheral, and DAC uses the DMA 1, channel number 7, stream 5 or stream 6, 5 for DAC 1, stream 6 for DAC number 2. So this table is pretty useful. The arbiter allows you to define priorities. You can have very high priority, medium, or low. So it's pretty much kind of similar to the interrupt routines. And in case of a tie, if two requests have the same software priority level, the stream with a lower number takes priority over the stream with a higher number. For example, stream 2 takes priority over stream number 4. Pretty straightforward. So let's go over this example. Let's go over a peripheral to memory mode. So the goal with this exercise is to have the ADC sampling values and then sending those values to the DMA controller. We're going to use DMA number 2 on channel 2 and stream 0 and 1, stream 0 or stream 1, and then we send that information to a volatile variable that the main is going to use to get the information from the ADC. We're going to disable the FIFO, so the value here goes directly to memory, one single instruction or one single burst here. The main function has initializing the microprocessor, initializes the ADC, starts the software conversion for one time, and then it just looks in a while one to this volatile variable and converts the value to a float number or an integer number. Inside of the ADC config, what we have here, so we're going to enable the DMA number 2. We're going to use the analog pin PA0. We're going to use ADC 3, so we have access to these pins over here. We're going to use PA0. So it uses GPIO-A, ADC number 3. So we enable all the clocks for those peripherals, and then we parameterize the DMA. And notice here that I have the volatile variable. I have the DMA pointing to that volatile variable, and the buffer size is just 1. It's not an array, just one of this type. I pick channel number 2, and I keep going. I disable the peripherals. I parameterize, disable the FIFO, so a couple of other parameters here, and then here define stream number 0. So we're using 0, and enables the DMA. And then let's configure the ADC. So we're going to use PA0, analog mode, and parameterize 12 bits. Notice here we are going to use the continuous convolution mode enable, so it's continuously converting, and it's going to use this trigger conversion, this external trigger conversion. And we assign here channel 0, so PA0 is on channel number 0, and it's PA0. We enable the requests, we enable the ADC and the DMA, and we enable the ADC, and we're good to go. So let's see an example of these working. Our second example, it's a DMA sending values to the DAC, so it's a memory to peripheral mode. Now what we have is a timer 6 is going to sample the DAC, that is going to get information from the DMA, and is going to put that information out. And that information is coming from an array of values that are initialized at the beginning of the program on the main. And we just point to those values, or to that array, and then the DMA just dumps those values to the DAC. Once again, we don't have the FIFO, sorry. We're using channel number 7, stream 6 and DMA 1 for our DAC 2. The example actually uses two DACs, DAC 1 and 2, which are going to use different streams, but the same DMA. So let's go over the main. We initialize the microcontroller, and here we enable the clock for DMA, we enable the clock for our GPIO-A and our DAC, and we set up the DAC channel 1 and 2, pin 4 and pin 5 of GPIO-A, and then we initialize the timer that is going to trigger your DAC, and we're just parameterizing a button using this new library STM eval PB init that is doing just these functions. It's just a library that you can use. So inside, keep going on the main function. Inside of the while one, what we have is we look at the button, if it's pressed or not is an external interrupt, and I affect the variable, and I affect which waveform am I selecting, either the 1 or 0, and I'm just going to cycle through different types of waves. Here it's just doing kind of a sawtooth wave, here it's a sine wave, so these two are passed by the constant arrays defined at the beginning of the program. If it's 0, it's the native ones, which is the noise and the triangle that you can just generate with the DAC. So let's go over just one example inside of the sine wave. The other ones pretty much work the same way. And I initialize here the DAC, and I'm saying that he's going to use this trigger from timer 6, and then I set up the DMA, and here I'm using stream 6, channel 7, and here this sine 12-bit, it's pointing to that const array with the values that I'm going to send. Notice that it's an array with 32 positions, so the buffer side now The buffer size now is 32. Here the direction, I'm saying that it's memory to peripheral. A couple of other parameters, and I enable the DMA, the DAC, and the DAC channel. And now inside of your timer number 6, all I need to do is enable the clock for the timer and kind of parameterize the timer to run and say that I want the timer 6 to go and trigger that source update that is attached or connected to the DAC. The timer is going to run around 328 kHz. It's just going to be your period, it does not have a prescaler, so it's pretty much whatever system core clock, which is 168 megahertz divided by 2, so we get 84, then 84 megahertz divided by 256, which is this FF, and gives you that value. So let's see this in action.